been a while, and I know you missed me. So why don't we build a robot together? To find out more, watch this video. Hi everyone, it's MJ Sanga, the creative engineer. In this video, we're going to build a 5 degree of freedom robot. Now, it is fun to talk about engineering concepts and engineering designs, but it's also important to physically build our projects. So this video will be a two-part, where in our first part, we'll first discuss the design, specifications, and the theory behind a robot arm. The second part of the video will mostly focus on building our robot, testing it out in the real world, and seeing how we can improve it. That will mostly happen when all our needed parts arrive. Now then, before we talk about our design of the robot and its applications, why don't we have a theoretical understanding of how robot arms work? Now, the main things that we need to understand when building our robot are the degrees of freedom, the kinematics, and the dynamics. Now, when we talk about the degrees of freedom in context of robotics, this refers to the number of independent movements a robot or a robot arm can make. Each degree of freedom represents a specific motion that a joint or link can perform. For the robot arm that we're going to make, the number of degrees of freedom determines its flexibility and its range of motion. Since we're building a 5 degree of freedom, it means that the robot can move 5 different ways. Now, the 5 independent movements that will be involved in this robotic arm will be the shoulder rotation, shoulder elevation, elbow joint, wrist pitch, and wrist roll. Each of these degrees of freedom will enable the robot to move in various rotations and positions within its workspace. This will allow our robot to perform various tasks and maneuvers. When it comes to kinematics, this mostly deals with the study of motion in a robotic system without considering the forces or the torques involved. This mostly helps us understand how different parts of a robot move relative to each other. In terms of the robot arm, kinematics is mostly applied in analyzing the joint angles and the link lengths to calculate the position and orientation of our end effector. Now, when it comes to robotics, there are 2 types of kinematic methods involved. There is forward kinematics and inverse kinematics. When it comes to forward kinematics, we determine the position and orientation of the end effector based on the joint angles and the link lengths that we already know. To explain this further, if we're already given the joint angle and the link length, we will use that to calculate the position of our end effector. This is mostly used when we need to calculate where our robot arm should move to perform a task. When it comes to inverse kinematic method, it's the opposite of forward kinematics. This is when we know the position and orientation of our end effector, but we do not know the joint angles that will produce that position and orientation. This method is mostly used in planning and controlling robot movements precisely, and for our robot arm, it's a method that we're mostly going to use. Our robot will be Arduino based, so when we are finding the desired coordinates or when we have the desired coordinates of our robot arm, we will use that to find the needed angles that will move our robot in the desired position. And when it comes to programming, inverse kinematics is mostly used. And the third thing that we need to know and understand is the dynamics of a robotic arm. When it comes to robotic dynamics, this mostly concerns the study of forces and torques applied to a robot arm and how these affect its motion. It's essential to understand how the robot arm responds to external loads and how to control it effectively. When it comes to robotic dynamics, it mostly shows us how velocity, acceleration, and torque are related within our robot. This helps us set limitations in which our robot can operate. These equations will help us design algorithms that will help our robot move smoothly and more accurately. Dynamics is crucial for several reasons. Number 1, motion control. Understanding dynamics allows you to control the robot's movements more precisely. For example, you can adjust the motor torques to ensure smooth and accurate motion. Another one is safety. Dynamics analysis helps us prevent overloading of joints, which could damage the robot or pose safety risk. This is very important if we want to build our robot to be maybe applied in manufacturing, the mines, or in agriculture. Another reason why it's crucial is because of energy efficiency. Efficient motion planning and control based in dynamics can help reduce consumption, which is important for battery-powered robots. Another crucial reason is collision avoidance. Dynamics can help predict and prevent collisions by adjusting the robot's path or stopping it in time. And lastly, feedback control. Dynamics information can be used in feedback control systems to correct errors in real time, improving the robot's performance. Feedback control is mostly important when it comes to automation, when we want our robot arm to perform specific tasks without the need of a human being to direct it. It's also important when it comes to machine learning and AI. The more the robot learns from the feedback, the more it will smoothly and accurately perform its tasks. Now, for this robot design, dynamics is crucial because it's mostly going to be controlled through programming. Understanding dynamics will help us design and create the needed code that will make the robot perform smoothly and accurately without any issues. By the way, if you're enjoying this video midway, please hit the like button and subscribe. Also, share this video to your fellow robotics engineers. Now that we've talked about the kinematics, the dynamics, and the degrees of freedom, we now need to move on to the end effector. The end effector is the part of the robot that is going to interact with the environment. For example, if we consider our arm to be a robotic arm, our hand will be its end effector. It will interact with the environment. The principle is the same when we talk about robotic arms. Essentially, most robotic arm end effectors are similar to hands, but I would like us to design something a bit different. This is where the application of our design comes in. Now, when it comes to applications, it's important and fun to build robots as an engineer. But as an engineer, we also need to solve solutions. So I would like the end effector for our robotic arm to at least solve one or more solutions out there. If possible, and we have enough materials, we'll design more than 2 end effectors that we can apply in the real world. Hopefully, in our second video, when we're physically building our robotic arm, I'll probably design a second end effector if we have the needed material for it. Now, the reason why I selected drilling, because when it comes to mining or machining or agriculture, it would be good to have a robot arm that is automated to perform certain processes accurately. So when it comes to drilling, maybe drilling into an ore mine to get a sample or drilling into some wood, that would be beneficial in most industries. It is also beneficial if our robot arm can drill into more than one part, meaning that if we would want it to drill into, let's say, more than 3 pieces, we would program it to do so, which will reduce time and make the person's work a bit more efficient. Now, robot arms have a wide application. They can be used in the hospital, they can be used in manufacturing, they can be used in machining, like I said before, and even in agriculture, not just for drilling, but just for the sake of building a robot and understanding it, we'll use drilling as its main purpose. Now, when it comes to drilling, this is the end effector that I designed using SolidWorks. It will be our base model for it, but I think over time, when it comes to finally building our prototype, a few design changes will be made. So now let's go to designing our robot arm. Like I said, I use SolidWorks mostly, but hopefully in the upcoming videos, I'll use other CAD softwares like Creo or Katia. But for now, we're mostly going to use SolidWorks. I first started by doing research on the types of robot arms out there. This made me decide to build a 5 degree of freedom robot. During my research, I also used it to theoretically calculate the torque forces for each link. This helped me decide on the motors to buy. After looking at a lot of 5 degree of freedom robots, I then designed a 2D sketch on paper to help me envision the robot that I want to build. I made it very simple so that I do not have any problems when it comes to 3D printing or CNCing each part. After that, I then went on to SolidWorks to build a prototype. Please note that this design is still under modification and simulation testing, but hopefully by the time the components arrive to physically build it, I'll have a final design to build. Now, we can calculate the inverse kinematics and the dynamics of our robot arm, but it's also important to simulate how the robot arm will work in certain operations. And this is where finite element analysis comes in. So for the finite element analysis, I mostly used ANSYS Workbench, and I mostly checked its temperature, the model analysis, and the static structure to see how loads are applied. So then, we come to what is known as bill of materials. This is a comprehensive list of components and materials that are needed to build our robot. In SolidWorks, you're able to create a bill of materials table of the assembly that you just made. The manufacturer will be able to know the quantity and the parts needed to build your final design. So then, the main components that we'll need for building this robot are 5 stepper motors. I picked NEMA 17 for this, 1 servo motor, cables, Arduino Uno, gear drives which will help in power transmission and torque increase, motor drivers for the NEMA 17 motors, and a potentiometer to control the speed of the motor of the drill. Because when it comes to drilling into a material, we need to know that the harder the material is, the slower the speed is required. This is mostly to help us preserve the material and to prevent things like friction that might cause deformation and wear and tear of our tool. One of the things that I want to try and do is program our robot to be controlled through a controller. No, not that controller, but a sophisticated controller. Most companies custom make their controllers, but I'll probably get an Xbox controller and use it to control our robot arm. If not, we can use inverse kinematics, where we put in the position of our end effector and its orientation, and we can then use the needed equations that will be provided to calculate the link angles. When it comes to the material that will mostly hold on to our robotic arm, since it's a prototype, I'm considering 3D printing it or CNC machining, but we shall see which is actually cheaper. At the end of our second video, I'm also going to talk about the final cost and the machining time and manufacturing it took to build this prototype. So that's it for part 1 of our video. I hope you guys liked it and you understood a few things about robots. If you want to learn the skills needed to build a robot, you can watch my video, the link provided right here. Or if you would like to subscribe and be notified of more of my upcoming videos, please hit the subscribe button and the notification icon so that you can be directly notified on more of my upcoming videos.